Hi there, guys. Well, welcome back. We're looking now at 5F, and the whole section is the justification of statistical techniques. But basically, this is about measures of dispersion. Now, we've talked a little bit about this before. We've talked about the range. We've talked about the interquartile range. And here we go. Here's a box plot. We've talked about the box plot a little bit before as well. A box plot, often drawn underneath a cumulative frequency graph, starts with your minimum value, ends with your maximum value, and in the middle, often with a dotted line for the median, but here with a straight line for the median. But overall in the middle, we can see we have this box which starts at the lower quartile and goes up to the upper quartile, Q3. Now, often you put an x-axis underneath this as well, just to show where it is and to show what it's relating to. These things are not always symmetrical. You know, the interquartile range might be at one end, might be at the other end. That tells you things about the distribution. But it's good to know that the interquartile range tells you about the spread of the middle 50% of the data. Okay, so that's the meaning of that distance of the interquartile range. So that is sort of possibly a more reliable measure of dispersion or spread, because more reliable than the range, because the range can be affected by outliers. Okay, well, I'm not going to do much on this because I want to get on to standard deviation and variance, and a couple of formulas there and applying those as well. But there's an example of a box plot. There you go. There it is. And we've also talked about outliers before as well. And so outliers, just take this thing again. Let's just remind people, hopefully remember as well, that an outlier is deemed to be, a point is deemed to be an outlier if you are beyond 1.5 times the interquartile range above the upper quartile, or 1.5 times the interquartile range below the lower quartile. So, I mean, I don't know what is the interquartile range there. We've got 4.5. You know, 4.5 times by 1.5. I mean, whatever that is. Okay, so whatever that distance is there, if we add that onto 7, and we can see that that's going to be bigger than 10. So 10 is not an outlier. That last point in this distribution is not an outlier. And it's possible that you get 2 outliers, you know, in which case then you have a problem. You think, well, do I include those things in this sample or not? You know, if they're not representative of my distribution, then what are they? Are they errors, or are they, you know, should I include them? What am I interested in? You know, so they create questions which you'll need to figure out. But, you know, maybe you take them out or maybe you don't. You have to figure out whether that's the right thing to do or not. And likewise, you know, if you take 4.5 times by 1.5 off 3.5, you see you're going to get a negative answer. Clearly, if the minimum value, the minimum result that you're getting is 0, that's not an outlier as well. Okay, outliers start from this point onwards. In this region here, the outliers. Okay, and likewise in this region here, outliers. Okay, there we go. Right, beware. Okay, so there's a little discussion of that, but that's not the big thing here. The big thing is variance and standard deviation. Because wouldn't it be nice if you had a measure of spread which didn't just take into account 2 data points, you know, maximum take away minimum, or third quartile take away first quartile. So that's all we've got up until now, but wouldn't it be nice if every point was counted in this spread of our data? And that's what the variance and the standard deviation becomes about. So let's just get rid of me. We don't need me really. And just zoom out a bit. Okay, so standard deviation and variance. Okay, so the range and quartiles are good measures. Our spread out a data set is around the median, but they do not use all the data values to give an indication of the spread. but these measures do. Now let's just build this one up. Okay, let's let's think about what we would ideally like. So if we've got all of our data points, if we've got x1, x2, x3, x4, what we'd not like to know is how far away they are from some central point. Well, what central point? We've got x1, we've got x2 there, maybe we've got x5 up here, we've got x3 here. How spread out are these things? And so I'm putting crosses and I'm putting marks. There we go. So it would be useful to know how far away this is from some central measure. Now, x3 is closer to some central measure than x1 is. But what central measure do we use? Well, we'll use the mean. That's kind of seems to be a fair thing to do. So we're going to use the sample mean here, take away x bar. Now, if we took away, I don't know where the sample mean is. Say, for example, it's here. I mean, I don't know, right? Say it's there. So if we take away the sample mean, so I don't know, say this is 2 and this is 5, and say that this is, I don't know, say this is 8, then when I do x1 minus x bar, I'll get minus 3. And when I do 8 minus 5, I'll get 3. When I add together all of these, I'll get this cancelling this out, and that's quite annoying because I want to know about my spread. So one thing I could do is I could take the modulus of this. That would seem to be a nice thing to do. That would make all of my differences positive. And in fact, that is a way of getting a measure of spread if I added all of those together, but that's not what leads to the standard deviation. Another way of making this positive is to square it. Now, that means that things which are further away have a far greater impact when we square those things compared to the things which are close in. So if this is 1 away and this is 3 away, then this squared is going to be 1 in this case, and it's going to be 9 squared in this case. So it's going to be 3 squared, which is 9 in this case. So the things which are further away have a much greater impact. Okay, yeah, well, okay, that's just a little thing to notice, really. So now if we summed all of these together, we'd get some measure of, how the how far away everything is from the mean all added together. But if we wanted to average those differences squared, we do this, okay? We average of all of those differences squared. Now we have what's called the variance. And the variance is, well, just what it is from the formula. It's the average of all of these x points, take away x bar, squared to make it positive, add them all together, all of those differences squared, and then divide by n to take the average of them. Okay, and then we'll have an average one of these things squared. Okay, well, since there's some squaring going on, the way in which we get to the standard deviation is say, well, let's square that. Okay, let's kind of make some attempt at undoing our average thing squared. And then we just get back to our average thing. Okay, so that's just a kind of intuitive way of looking at it. That's not a proof or anything. In fact, it's difficult to say that these things can be proved, really, because they're just statistics. There, someone said this is kind of a good idea. Why not? Let's do this and let's see where this leads. But it is based on some mathematical logic. So anyway, this thing is called the variance, and the variance we call sigma squared. Or actually, sometimes we call it S squared, standard deviation squared. But we need to talk about that as well, actually. So here we go. That's called the variance. So this is the variance. This is the variance, okay? And variance doesn't mean, what it does in English. It doesn't mean, how does this thing vary with this thing? I mean, it sort of comes from that, but it's a definition. Like dy dx is a definition. The variance is a thing. It's a particular thing based on a formula. So that's how it's defined. in mathematics. Now, this is the variance for when we're using a sample, but there's a slight correction that we do when we're using it for a population. In fact, with a population, we divide by n minus 1. And I don't want to go into that too much just at the moment, but it's basically about degrees of freedom. Right, when we do this n times over, we're doing it from 1 to n, and we've got 9 results, but we've only actually got 8 degrees of freedom. What's called 8 degrees of freedom. We're basically, because we keep using x bar, and x bar is dependent on everything else, that takes away. That means we've got 9 results, but they're all dependent on one result, which comes from the 9 observations anyway. So it turns out we have 8 degrees of freedom. So in fact, we need to divide by n minus 1. That's a tricky little concept, and there's a lot of maths behind that, in fact. So I'm not going to go into that too much just at the moment. So anyway, at the moment, this is our variance. This is for the sample distribution. Okay, sample that we have, sample of x values. Okay, now the standard deviation was just, to get to the standard deviation, it's just this. This is sigma. Okay, this is capital sigma, something like this. And in Greek, lowercase sigma is this, and it's used to define standard deviation of a sample. Now, sometimes it's called sigma n, and sometimes you'll get sigma n minus 1 for your population standard deviation. But again, I'm not going to go there just at the moment. I'm just going to say standard deviation is sigma. So how do I get that? Well, I need to square root my variance. So this now is equal to what's called, and again, just the definition, it's called the standard deviation. Okay, and we'll look at some results based on standard deviation in a bit. So there's another thing that you need to know here, and it's that this can be done in a nicer way. Okay, so I guess we really need to look at, let's look at an example, okay? So let's look at an example. Let's say there's some x values here. So let's say that the set of values which we have are going to be 2, 5, 6, 7, and 10. Okay, 6, 7, and 10. This is just an example I came up with myself earlier on. Okay, now what we can do is say, well, let's put in each of these values. 2, 5, 6, 7, and 10. I've got 5 values there. Those are my xi's. And then I can do xi, not ii, xi, take away x bar, and then squared. Now what's x bar? X bar is equal to all these things added together, which is 30. 30 divided by 5 is just 6. Okay, so what I'm going to do is take away 6, that leaves me with 4. Square that. You don't need to worry about the negative signs. It's taking us to 16. Same thing for the next one. 5 take away 6 is 1, or minus 1, and square it is going to leave us with 1. Like for the next one, we're going to get 0 squared. The next one, we're going to get 1 squared. And for the next one, we're going to get 4 squared again, so 16. Okay, so there we go. That's the sum of that. That's all of our xi's minus x bar squared. Now we need to sum all these things together. And if we sum all of these things together, we get 34. So what's the variance? Well, the variance, which is a measure of spread, as is the standard deviation. So the variance here is going to be equal to 34. So it's the sum of your xi's, take away x bar, squared, divided by n. Divided by n. So we're going to do 34 divided by 5 there, and that's going to bring us to 6.8. So the variance is 6.8. Now, we have really no idea how good that is. But again, remember that's like the average difference between the xi value and the x bar squared. So that's the average version of the difference squared, if you like. Now, if we square root that, we standardize that variance, if you like, and that's what we're calling the standard deviation. So we can clearly square root this and we'll get the standard deviation. But again, we don't really have a lot of sense as to how good that is. And again, I'll talk about that a bit later on. Talk about, how many in a distribution, how many values you expect within one standard deviation of the mean. I'll be talking about that in a bit. I've just written this out again because this program strangely crashed. But what I was going to talk about was this, and talk about the fact that in the formula book, you've got two different versions here. So the standard deviation, if you look at where it says standard deviation there, you can see that it's got the square root of, and that's very similar to what we've written down here. Apart from they've got this extra f here, and they've called this mu. Now, it's debatable whether they should have called that mu, but you just have to understand that mu is essentially your mean. Now, having f here, just look at that again. So you see where they've got the f there, the standard deviation on that second formula, which you can see. So f of, in brackets, xi minus mu. So where they've got that f, so like here, it's basically saying, well, look, if you've got this multiple times, there's no need to, do each thing separately. Maybe if you have 16 100 times in this list, then you're just going to do 100 times 16. So it's just a way of speeding things up if you have essentially a frequency table. Okay, and that f also exists in the top one there as well. Now, the top one is kind of interesting because they say, well, here's the variance, but it's in a different format on the right-hand side there. So again, they're saying fi and then in brackets xi minus mu all squared, but then look to the right-hand side there and they're giving you this alternative version. They're saying fxi squared over n minus mu squared. Okay, well, I've not given you that, but I am going to show you that. I'm going to show you that it works as well. Now, what I'm going to do is take the variance here. Okay, I'm going to try and prove it for you. Okay, so here's the variance. We've got the sum of xi minus x bar all over n. If I multiply this top line out, I'm getting the sum of xi squared. So I'm essentially saying, well, let's actually use another line here. Let's say xi squared minus 2 lots of xi x bar, and then add x bar squared. Yeah, that's fine. And then divide by n. Now I'm going to bring that sigma on the inside. I'm going to say we've got sigma xi squared. Okay, so I can do that. I can split this sigma into multiple parts. And then I'm going to say minus, and here I'm actually going to take out the 2 and the x bar because that doesn't rely on I. I is essentially here, I between 1 and n, but I'm just not putting it in for the moment because it's be even more scruffy than I am already. Then we're going to say here, I'm going to bring the sigma on the inside for my xi's, and then I've got my plus sigma lots of x bar squared. Okay, so now I've got this, and now I can say I've got sigma xi squared all over n, take away, and now I've got 2 lots of, and I'm going to bring like this together, and I can see that I've got sigma xi over n is actually x bar. So this is really giving me 2 lots of x bar squared. That, if I incorporate that, the n with the sigma xi gives me the definition for x bar. And then I've actually got on here, yeah, I think I've still got this. Yeah, so I've got here, I've got n lots of, see I'm doing this every single time I go through, I'm going for I is 1, I is 2, I is 3. I'm doing this n times. I'm adding this thing, which is just a constant, n times over. So I can call that n x squared. But remember, I've still got to divide that one by n as well. So it's divide by n, so that's now going to cancel. Now you can see I'm getting this other formula out, getting sigma xi squared over n. So that's the sum of my values squared, my data points squared, but the average of that. So the average of my values squared, the average of my values squared, yeah, that makes sense. Okay, and then we're going to do minus x bar squared here on the end, because we've got two lots and we've got one lot, and this is obviously taking away. So this is the average of your values squared added together, sum of your values squared, and this is the square of your average. And we've got to subtract in the center there as well. Now we can do the whole thing, this sigma squared, like this instead. In fact, this turns out to be nicer a lot of the time in tables. Actually here it doesn't make too much difference because the numbers are smaller, but if we just do xi squared, we've got 4, 25, 36, 49, and 100. If we sum all of those xi's squared, I was going to put in this column, then we're getting a total of 214. And now we can say, let's do 214 divided by 5, take away, and what was x bar? X bar was 6. So take away 6 squared, and you'll find out that that's also equal to 6.8. Okay, so there's a different way of doing the variance over here. It's using this formula here. So it's kind of easy to see, I suppose, because you can essentially separate out this and this. But look, that's no longer over n. Okay, so yeah, so you can hopefully remember this little formula here. You've got two versions. That's kind of how we built it in the first place, and this is a rearrangement of it, which is often useful. Okay, well, in the book, now they're talking about a little investigation here, and then they're going on to define the population standard deviation and the population variance. Yeah, okay, so that's interesting. Putting in their x minus mu. So they're saying, well, this is our population standard deviation. They're putting mu in. Yeah, okay. This is what we were talking about earlier on, and in fact, if we put in x bar, then that's the sample standard deviation, because we're just reducing the population down to the sample. Now, what I was talking about earlier is turning up later. That's saying, well, if we've got the sample standard deviation, we can make a correction on it to make it the population standard deviation. Now, interestingly, here they're calling sigma the population standard deviation. Now, often you'll find out that they'll say sigma n minus 1. But okay, sometimes they use s, sometimes they use sigma. And here they're saying sigma is equal to the population standard deviation. But you can call that the sample standard deviation as well if we're taking away x bar rather than mu. Okay, the correction I'm talking about is going to happen later. It's in a later exercise. Okay, so it says if the data set is close together, the standard deviation will be large. If the data set is spread out, the standard deviation will be large, vice versa. Okay, I think I misspoke there. Standard deviation will be small if the data set is close together, quite obviously. The units of standard deviation are the same as the units of the original data. Okay, now there's an example 7, which you can have a go at. And they're also giving you an example of this through technology. And you'll notice here that they're picking on sigma x and not sx, because you'll see that in SX, when you're going through the table, just zoom in a little bit here. Okay, you can see that there's above the red square, the red block that they've come up with, there's SX, and you'll see that that says SN minus 1. That's the correction to the to this if it's a sample, which again I'm going to talk about later. So if this is our population, or if we're just interested in finding out the sample standard deviation, then we can use the thing which is blocked out in red there, the sigma X. Okay, so yeah, so there you go. That's one variable statistics. Your calculator will give you that. And that's done, and then there's a little investigation. Oh, and then there's another bit here saying the number of text messages given by 15 students in 1 week. Find the mean and the median number of text messages. Find the interquartile range. Determine if any of the values can be considered as outliers. Well, again, I'm not going to talk about that too much. I've talked about that already. If we've got the upper and lower quartile, we can easily do 1.5 times that and add 1.5 times the interquartile range and add that onto the lower quartile, the upper quartile, and take it off the lower quartile and see if we're outside of that range. We've talked about that. I'm not going to do this one now, but you can see it's there. Now, what I do want to do, though, is just talk about the meaning of this standard deviation. Okay, so let's get rid of all of this. It might be worth just writing down the fact that we've got this is one formula for the variance, and this is the other formula. Okay, but it is given in the formula booklet. It's just given with an F there as well. Now, should talk a little bit about what standard deviation means as well. Now, if your sample is distributed, or your population is distributed normally, and that's a big if, in fact. But if it's distributed normally, that's to say it's like this bell-shaped curve. It's not skewed this way positively or this way negatively. Okay, so if it's like this, and if you've got thousands and thousands of pieces of data, then all your histogram is going to start looking really, all your bars are going to start looking really small, and you're going to get this kind of normal distribution. Now, if your data is normally distributed, then we can say there is a meaning to the standard deviation. And that's to say that within one standard deviation of the mean, so say, for example, the average of people's heights in the class is 170 centimeters. And say maybe we're saying, well, I don't know, maybe the standard deviation is, that's a bit big. Let's do 160. The standard deviation here is going to be 10 centimeters. And that's what they were saying when they were saying in the book that the units for the standard deviation is the same as the units on this axis here, the variable units. Okay, so maybe this is our standard deviation. Okay, maybe the variance was 100, and maybe that's our standard deviation. Now that has a meaning because there is a certain percentage of all values which are expected to lie within one standard deviation of the mean, and it's something like 68%. But I forget a little bit. Okay, so let's just check this one out. But it basically gives us a meaning for this. So how much data lies within? Oh, there we go. I had it there. One standard deviation. Okay, here we go. So if we just zoom in on this a little bit. So let's zoom in a little bit here. And you can see it says for an approximately normal data set. So again, that's what I'm talking about here when I say it's not necessarily a normal distribution, but if it's approximately normal, then we can say that the values within one standard deviation of the mean account for about 68% of the set. Woohoo, I remembered it. Okay, so account for about 68% of the set. About, they're saying about because it's approximately a normal distribution. And the better and closer you are to a normal distribution, the more you can say that data is true, that information is true. And then it says, well, within 2 standard deviations, 95% of the data is accounted for. So that is to say that, between 150 centimeters, and so we're just adding on these amounts of standard deviation, and 190 centimeters, that would now be between, okay, up until here. So all of this, Norwich City colours here, all of this would account for 90, what did it say? 95%, okay, 95%. I forget these numbers. And within 3 standard deviations of the mean, you expect almost all of your data to be accounted for. So that's the sort of rough meaning of what standard deviation is. There you go, they're calling it the 68, 95, 99.7 rule. Okay, so if we went back to our question where we had 2, 5, 6, 7, and 10, and we found out that 6.8 was the standard deviation. No, it wasn't. That was the sigma squared. That was the variance. And if we now say the standard deviation, let's take the square root of 6.8, and that's giving us, so sigma, or the standard deviation, in other words, is 2.6 roughly. Okay, so 2.6 within the mean. Well, within 2.6 of the mean here, we have 5 and the 7, but not the 2, not the 10. So actually, we have 3 out of 5 values. We actually have 60% of values in between 1 standard deviation of our mean. The mean being 6, 1 standard deviation is this. 2.6 on the side of this includes this and this, but it doesn't include this and this. Now, I set this one up deliberately to be a bit like a normal distribution. Okay, I've set it up where I had a 2 and more values near the center, and then these kind of few values towards the edge, if you like. So I kind of set that up a little bit deliberately, but 60% is not far off 68%, and 68% obviously would be impossible to get from 5 values. But you can see the idea that really 68% of the data should be within 1 standard deviation of the mean, if it's normally distributed. Okay, guys, well, I'm going to stop there. I think I need to go and have a drink, by which I mean a cup of tea. There we go. You can see these questions. You can have a go at those questions as well, but they're basically everything I've talked about. And so in example 5F, only 4 questions there, but really important that you get some practice with having a go at the standard deviation through the 2 formulas and also on your calculator. Most of your, one extra thing. Yeah, good. So for question 2 here, let's have a little look at this one. This is a classic type of question. Because you don't have much time in an exam, because you have non-calculator exams, you think, well, this definitely can't turn up non-calculator. Yes, it can, because you can use that formula, f of x, sigma f of x squared over n minus x bar squared is equal to your variance. We've got enough information here to work out the mean by doing this divided by this, and then also to work out this here, and we can then work out our standard deviation. N is equal to this as well. So we've got enough information to work out the standard deviation by just doing a small calculation here. You probably do need your calculator for that, though. Okay, well, there we go. That's me done. Good luck with this exercise, and hope to see you back for the next one.